Namaste, myself Mr. Birajdar, Assistant Professor, Department of Humanities and Science, Walchand Institute of Technology, Solapur. In this video lecture, we will discussing applications of first order and first degree ordinary differential equations to Newton's law of cooling. Learning outcome. At the end of this session, students will be able to solve problems on Newton's law of cooling. Now let us start with statement of Newton's law of cooling. It states that the rate of change of temperature of the substance is directly proportional to the difference in the temperature of the substance and the temperature of the surrounding medium. Now this statement can be converted to mathematical equation. For that, let us suppose theta is used to denote the temperature of the substance at any time t. Theta naught is used to denote temperature of surrounding medium. Then by statement of Newton's law of cooling, d theta upon dt is nothing but rate of change of temperature with respect to time t is directly proportional to theta minus theta naught. It can be written as d theta upon dt is equal to minus k in bracket theta minus theta naught. Denote this equation as 1. In this equation, k is the constant of proportionality and negative sign indicates that due to cooling of temperature. Now this differential equation can be solved by two different methods. One is by method of solution of linear differential equation and another one is by method of separation of variables. Now here in this session it is solved by method of linear differential equation. Before that, pause a video for a while, write answer to this question. Question is, write a formula of solution of a linear differential equation of first order and first degree of type dy by dx plus py equal to q. Come back. I hope you written answer to this question. The answer is the solution of linear differential equation of dy by dx plus py equal to q can be obtained by y into if, which is equal to integration if into q into dx plus c, where if stands for integrating factor of the differential equation and it is obtained by formula if equal to e power integration of function p with respect to x. So this is we learned in unit number 1. Now this method is used to solve a mathematical equation of Newton's law of cooling. Solution. So our Newton's law of cooling differential equation is d theta by dt equal to minus k into bracket theta minus theta naught. This equation can be written as d theta by dt plus k into theta is equal to k into theta naught. This differential equation is linear differential equation with theta is dependent variable. Here capital P is k and capital Q is k into theta naught. Now integrating factor of this differential equation if equal to e power integration of function p dt. Put the value of p equal to k in this. So we get if equal to e power integration of k dt. It gives if equal to e power k constant outside and integration of dt is t, so that integrating factor is equal to e power k into t. Now general solution formula for this equation is theta into if is equal to integration of if into q into dt plus c. Substitute the value of if and q in this solution. We get theta into e power kt equal to integration of e power kt into value of q is k into theta naught into dt plus c. Therefore, theta into e power k into t equal to In the right hand side, k into theta naught constant taken outside, and integration of e power kt with respect to t is e power kt upon k, and plus c constant of integration. This is after dividing e power kt on both this side, and in the right hand side k gets cancelled. We get value of theta equal to theta naught plus c into e power minus kt. This is can be written as theta minus theta naught is equal to c into e power minus kt. So this is the required general solution of a differential equation of Newton's law of cooling. Now with the help of this solution, we can solve some examples. Now example number 1. At a room temperature 25 degrees Celsius, the temperature of a body is 75 degrees Celsius. After 15 seconds, the temperature of the body was found to be 65 degrees Celsius. Find its temperature after 90 seconds. Solution. Let us denote theta be the temperature of body at any time t, theta naught be the temperature of surrounding medium. Here given that value of theta naught is 25 degrees Celsius, and also given temperature of that body theta equal to 75 degrees Celsius at t equal to 0 second, and temperature theta equal to 65 degrees Celsius at t equal to 15 second. Now we are asking value of temperature theta when time t equal to 90 second. For that we start with Newton's law of cooling, whose its differential equation is d theta by dt equal to minus k times theta minus theta naught, where its general solution is theta minus theta naught equal to c into e power minus kt. But theta naught equal to 25 degrees Celsius given, put in this general solution, we get theta minus 25 is equal to c into e power minus kt. Denote this equation as 1. We also given that theta equal to 75 degrees Celsius when t equal to 0 second. Put in equation number 1. We get 75 minus 25 equal to c into e power 0. This gives value of constant c is equal to 50. Substitute this value of c in equation number 1. We get theta minus 25 is equal to 50 into e power minus kt, and denote this equation as 2. Now we also given that theta equal to 65 degrees Celsius at t equal to 15 second. Substitute these two values in equation number 2. We get 65 minus 25 equal to 50 into e power minus 15k, which gives 40 equal to 50 into e power minus 15k. From this we get value of e power minus 15k, which is equal to 40 upon 50, but 0 gets cancelled, it gives 4 upon 5. So this is the value of e power minus 15k, and denote this equation as 3. Now we have to find value of theta at a time t equal to 90 second. For that, put t equal to 90 in equation 1, that is in equation theta minus 25 equal to 50 into e power minus kt. We get theta minus 25 is equal to 50 into e power minus 90k. From this we get theta equal to, take this minus 25 to right side, becomes 25, and plus 50 into bracket e power minus 90k can be written as e power minus 15k bracket raised to 6. This is by using laws of indices. Then theta equal to 25 plus 50, but the value of e power minus 15k is 4 upon 5 from equation number 3. Substitute here. So we get theta equal to 25 plus 50 into 4 upon 5 bracket raised to 6. And after simplifying this, we get value of theta equal to 38.1072, and approximately we write it as theta equal to 38 degrees Celsius. So this is the required answer for the given question. To prepare this video lecture, I refer this book as references. Thank you.